Welcome to Mr. Baker's House of Knowledge.
Yay! Okay, here we are at Mr. Baker's House of Knowledge, the place where great learning occurs. I know this because you will find this link on Edmodo later, and Edmodo is where learning happens. We'd like to thank our friends at YouTube for putting this on for us as well. I feel like I covered everything there. All right, so we're going to talk today about the perpendicular bisector theorem. The perpendicular bisector theorem is basically a theorem that states if you already have a perpendicular bisector of a line, then if you go and put a point anywhere on that line, then the two segments that occur from that will be congruent because they're going to be equidistant from the endpoints. And I'll illustrate what that means in a second. And then we've got the converse of the perpendicular bisector theorem, where if you have a point that's equidistant from the endpoints and you draw the distance from this point to the line, that distance is the perpendicular bisector. Now, we need to understand that when I'm talking about a point and a line, there are many, many, many ways that I could draw a line from a line to a point. So I could draw a line from here. I could draw a line from here. The thing that we need to understand is when I talk about the distance from a point to the line, it's the shortest possible that it could be, and that distance is always perpendicular. So if you're talking about the distance of a point, which is one-dimensional, and a line, which is two-dimensional, the distance is always perpendicular. And that's important to know. All right, so let's take a look at a situation where we've got a perpendicular bisector. So this line right here is a perpendicular bisector of segment AB because not only is it perpendicular to segment AB, but it cuts AB in half at this point right here, and I think I'll call that point O. All right, so what I'm going to do is Eli's going to help me out here. I'm going to put my pen at the top, and I'm going to slowly move my pen down the line. And Eli, I want you to, at some point, randomly just tell me to stop. Are we ready?
I'm ready.
All right, here we go.
Stop.
All right. So I'm going to call this point E for Eli. Alex, I'm not going to use you because your name starts with the letter A. So we'll move on to Lexi. Lexi, we're going to do it again. I'm going to trace down, and when you want me to stop, just say stop. The only thing I don't want you to try to stop me on is don't stop me on point E or point O. We ready? Here we go. Right here. All right. So we've got point E. Now point E lies on the perpendicular bisector of AB. So I know that point E is actually going to be equidistant from the endpoints of that line. It's going to be equidistant from A, and it's going to be equidistant from B. Okay? So that means that that is congruent to that. And the reason is because of the perpendicular bisector theorem. So I could say in this particular situation, AE is congruent to EB by the perpendicular bisector theorem. Now, remember, you had to know some stuff before you can use the perpendicular bisector theorem. And the things that you have to know is that this line is the perpendicular bisector of this line. All right, we're going to call this point L, and we're going to do the same thing. Yes, ma'am.
Could my point have gone like after the O? Because I thought I was just doing that little line thing.
Okay, so that's a good question. In fact, why don't I move your point?
Yeah, because I was just, move that.
We'll take your point. We'll throw it down there. How's that sound?
I think I like that one better.
All right. So we'll move point L to there. And we'll go ahead and connect those to the endpoints. And what do you think you're going to know about AL and LB? Right. Now, here's a question I've got for you. Is triangle AEB congruent to triangle ALB? And if so, tell me which of the 3 ways to prove, or which of the 5 ways to prove triangle is congruent that is. So somebody said side angle side. All right. So tell me which sides and which angles are congruent.
Isn't it congruent to itself?
AO would definitely be congruent to itself. AO is neither a side in triangle LB or AEB. So I'm looking for triangle.
Oh, then AB.
So AB is congruent to itself. I would agree with you. By reflexive, AB equals AB. Or AB is congruent to AB. So that's a side. Now what angle do I have congruent? Or what sides do I have congruent?
2 other ones.
So you're saying that AL is congruent to AE?
I think the angle in the middle is, wait, which triangles? The top triangle and the bottom?
The yellow triangle and the triangle not highlighted.
Well, they both have the perpendicular bisector in common, so they would both have 90 degrees in the middle.
Okay, but 90 degrees, these 90-degree angles, none of these 90-degree angles are angles of this triangle.
Oh, yeah. Okay.
So I'm ignoring that information. Basically, I'm asking you why you're telling me that that triangle and that triangle. So here's A, here's B,
Is EO
here's E, here's A, here's B, and here's L. And the only thing that we've said so far that I agree with is that that is congruent to that. Oh, by the way, we know that this is congruent to this, and this is congruent to this.
Yeah, but those aren't congruent between both of them. That's just in that one triangle.
Right. So the only way that these 2 triangles would be congruent is if this length and this length were the same. So to illustrate, Lexi could have said, hey, I really want to put my point down there. And so her picture would have looked like this. And now it's really obvious that those 2 triangles aren't congruent. So it's still, L is still on the perpendicular bisector, so those segments are still congruent to that segment, but it does not imply that the top triangle and the bottom triangle are congruent. Now, you could probably make a great argument for the left triangle and the right triangle to be congruent in either situation by hypotenuse leg. But the top and the bottom don't necessarily have to be. In fact, this diagram AEBL is a special quadrilateral called a kite, and we'll learn about that in Unit 6. All right, so here's what I want you to do. I want you to use the perpendicular bisector theorem, and I want you to find me the value of AB. So go ahead and work on that, and I'm going to pause the video. You can pause it at home. All right, so what do we know about BA and BC, or AB and BC? Somebody said that they were congruent. How do we know that? By the perpendicular bisector theorem. So the perpendicular bisector theorem lets us know that this line right here is congruent to this line right here because this point B lies on the perpendicular bisector. If a point lies on the perpendicular bisector, it will be equidistant from the 2 endpoints. So the 2 endpoints were A and C. That means AB and CB are congruent because B is equidistant. Equidistance means same distance. So now that I've set this up, that means that AB is equal to BC, and I can just plug stuff in. So here we're back to a situation where we've got 2 expressions up there that are going to equal each other. You're going to have to know the difference between when stuff equals each other and when you have to multiply something by 2. So this section has a little bit more thought going to it. It's not, oh, every time I see a bunch of numbers, I can just set them equal to each other. You have to actually think about what's going on. Then when we solve for this, I'll subtract 6x from both sides. I'll get negative 2x is equal to negative 10, and I'll get x is equal to 5. Now, it asked me for the length of AB, so AB is equal to 4 times x. That's going to be 4 times 5. 4 times 5 is 20. So the solution to this problem is that AB is equal to 20. How do we feel about that? Thumbs up if we're okay. Thumbs down if we're not. Maddie can just lay her head down on the desk and ignore me.
Do what?
Yeah, exactly. All right, so the other thing I want to talk to you about is the angle bisector theorem. The angle bisector theorem says that if you bisect an angle, that any line, any point on that bisecting angle line is going to be equidistant from the two sides of the angle. Now remember, equidistant implies perpendicular length. So if QS bisects angle PQR, and we're looking at SP and SR, the distance between the two lines, that means they're perpendicular, then these two will also be congruent. Conversely, if we have a situation where we've got a point that's equidistant from two lines, then if you draw a line through the vertex of that angle and that point, you will get the angle bisector. So how is this going to play out? Let me just do a quick example for you here. So if I were to have an angle, and we'll call this angle JEP. Angle JEP. If I have angle JEP, and then I have a point out here called K, and I know that line segment EK bisects angle JEP, then any point that I pick on EK is going to be the perpendicular, its distances to these two sides are going to be equal. So to draw a distance, I need to make sure that my line is perpendicular. Change color. So try to get that as close to perpendicular as possible. So I know that these two line segments are going to be equal. So if I say that this line segment was 2x, and I say that this line segment was 30, then I should be able to find the value of x. Because this is an angle bisector, that means that is congruent to that. So we can set up the equation JO is equal to OP. And I really want you to get in the habit of writing the segments down and then substituting in. Substitute in JO, 2x, substitute in 30 for OP, 30 must be overpowered, and x will equal 15. Thanks. Thanks. All right, so I don't really have time to lead you through a guided practice, so what I'm going to do is I'm going to put an assignment up on SchoolNet. And I want to make sure everybody can get to that. It's a tutorial that'll take you through some guided practice and let you to practice this stuff on your own. And then for tonight, your homework is listed here.